So similar to the Thevenin's theorem, this Norton's theorem is used to simplify the complex network. And in fact, this Norton's theorem is the dual of the Thevenin's theorem. And it will get clear to you very shortly. But before that, first of all, let us see the statement of the Norton's theorem. So according to this Norton's theorem, any linear network can be replaced by the equivalent network which contains the current source in parallel with the impedance. So let's say there is some network N, and using this Norton's theorem, it can be replaced across these two terminals by the equivalent current source IN in parallel with the equivalent impedance. So here IN is the short circuit current, and it is the current which flow through these two terminals A and B when they are short circuited. Similarly, this Zn is the Norton's equivalent impedance, and it is the equivalent impedance which is seen through this terminal A and B when all the independent sources in the network are 0. That means while finding this equivalent impedance, all the voltage sources in the circuit will be considered as the short circuit, while all the current sources will be considered as the open circuit. And using this, we can find the equivalent impedance. So this equivalent representation of the network is also known as the Norton's equivalent circuit. So now let us see the steps using which we can find the Norton's equivalent circuit for the any network. So first of all, for the given network, find the short circuit current between the terminal A and B. Or in general, find the short circuit current between the two terminals across which you want to find the equivalent circuit. Now in the second step, if the circuit contains only the independent sources, then consider all the independent sources as a 0 and find the Norton's equivalent resistance between the terminal A and B. But if the circuit contains both independent and the dependent sources, then directly we cannot find the equivalent resistance. So in that case, first of all find the open circuit voltage or the Thevenin's equivalent voltage across the two terminals. And the ratio of this open circuit voltage to the short circuit current gives the equivalent impedance. So when the circuit contains independent as well as the dependent sources, then using this method we can find the equivalent impedance. Alternatively, for the given network, first of all we can find the Thevenin's equivalent circuit, and then using the source transformation it can be converted into the Norton's equivalent circuit. So here the Norton's equivalent resistance or the Norton's equivalent impedance is same as the Thevenin's equivalent impedance, while the Norton's current IN can be given as VTh divided by ZTh. And in fact, if you see the Thevenin's as well as the Norton's equivalent circuit, then they are the dual of each other. So that is being said, now let us take some examples on the Norton's theorem. So in the first example, we have been asked to find the Norton's equivalent circuit across these two terminals A and B. And for that, first of all let us find the equivalent resistance across these two terminals. And for that, let us consider all the independent sources as 0. So here, this 2 ampere current source will act as an open circuit, while the 12 volt voltage source will act as a short circuit. And considering this, now let us find the equivalent resistance which is seen through the terminal A and B. So now if you see over here, these three resistors are connected in the series connection. That means their equivalent resistance Rs will be equal to 4 ohm plus 8 ohm plus 8 ohm. That is equal to 20 ohm. And that 20 ohm is once again connected in parallel with the 5 ohm resistor. So the equivalent resistance which is seen through this terminal A and B will be the parallel combination of this 5 ohm resistor and the 20 ohm resistor. That means Zn will be equal to 5 ohm in parallel with 20 ohm. That is equal to 5 times 20 divided by 5 plus 20 ohm. That is equal to 4 ohm. That means the Norton's equivalent resistance which is seen through this two terminal A and B is equal to 4 ohm. And once we have found this equivalent resistance, then let us find the short circuit current which is flowing through the terminal A and B. And for that, let us short this terminal A and B. So once we short this terminal A and B, then this 5 ohm resistor will also get short circuited. And in this condition, the equivalent circuit will look like this. So in this circuit there are two loops, and let's say the current which is flowing in these two loops are I1 and I2. Now if you see over here, clearly the current I1 is equal to 2 ampere while the current I2 is equal to ISC. So considering this, now let us apply the KVL equation in this second loop. So applying the KVL equation, we can write 8 ohm times I2 plus 8 ohm times I2 minus 12 volt plus 4 ohm times I2 minus I1 is equal to 0. That means 20 times I2 minus 4 times I1 is equal to 12 volt. Now here this I2 is the short circuit current and the I1 is 2 ampere. That means from this we can say that 20 times ISC is equal to 12 plus 4 times 2 ampere. Or in other words, this short circuit current is equal to 1 ampere. Or in other words, this Norton's equivalent current is equal to 1 ampere. So in this way, for the given circuit, the Norton's equivalent current is 1 ampere while the Norton's equivalent resistance is equal to 4 ohm. And this is the equivalent representation of the given circuit. So now let us take the second example where the circuit contains both independent as well as the dependent sources. So as I mentioned earlier, when the circuit contains both independent as well as the dependent sources, then what we will do, first of all, we will find the short circuit current between the two terminals, and then we will find the open circuit voltage. And the ratio of this open circuit voltage or the Thevenin's equivalent voltage to this short circuit current will give us the equivalent resistance. So for that, first of all, let us find the Norton's equivalent current or the short circuit current between the two terminals. Now if you see over here, once we short these two terminals A and B, then this 5 ohm resistor and this dependent current source will become parallel to this portion of the circuit. That means now the voltage across this 4 ohm and the 5 ohm resistor is equal to 10 volt. And from this we can say that this current Ix is equal to 10 volt divided by 4 ohm, that is equal to 2.5 ampere. So now to find this short circuit current, let us apply the KCL at this node. So if we apply the KCL at this node, then we can write this short circuit current ISC is equal to 2 times Ix plus the current through this 5 ohm resistor. That means short circuit current is equal to 2 times Ix plus 10 divided by 5 ohm. That means the short circuit current ISC is equal to 2 times 2.5 ampere plus 2 ampere, because here the value of current Ix is equal to 2.5 ampere. That means the short circuit current ISC is equal to 7 ampere. So in this way we got the value of this short circuit current or the Norton's equivalent current. And similarly, now let us find the open circuit voltage. Now here this open circuit voltage is the voltage between this node A and B. That means this open circuit voltage VOC is equal to VA minus VB. But here, as this node B is the reference node, so the voltage VB will be equal to 0. That means voltage VOC is equal to VA. That means to find this open circuit voltage, we need to find the voltage at this node. So here, let's say this node is X and the voltage at this node is equal to Vx. And clearly if you observe, this voltage Vx is equal to 10 volt, right? So now to find this voltage VA, let us apply the KCL at this node. So here, let's say the current which is flowing through this 5 ohm resistor is going away from the node. And if you see over here, this current from the dependent source is actually entering the node. So if we apply the KCL at this node, then we can say that the current which is leaving the node is same as the entering current. That means 2Ix is equal to voltage VA minus Vx divided by 5 ohm, where VA is the voltage at this node. So here the value of Vx is equal to 10 volt, while we have already found the value of Ix as 2.5 ampere, right? That means from this we can say that 2 times 2.5 ampere is equal to Va minus 10 volt divided by 5 ohm. That means the value of Va is equal to 35 volt. Or in other words, we can say that the open circuit voltage VOC is equal to 35 volt. So in this way, we got the value of VOC as 35 volt, while the value of the short circuit current is equal to 7 ampere. That means the Norton's equivalent resistance is equal to 5 ohm. So for the given circuit, the short circuit current or the Norton's equivalent current is 7 ampere, while the Norton's equivalent resistance, which is seen through these two terminals, is equal to 5 ohm. And this is the Norton's equivalent of the given circuit. So similarly, let us see the third example where the circuit contains only dependent sources. So when there is no independent source in the circuit, then the Norton's equivalent current or the Thevenin's equivalent voltage for such circuit will be 0. But in this type of circuits, we can find the equivalent impedance which is seen through the two terminals by applying either a test current or the test voltage between the two terminals. So if we apply the test current, then we need to find the voltage across this test current. And the ratio of this voltage to the test current will give us the equivalent resistance. Similarly, if we apply the test voltage, then we need to find the current which is flowing through this voltage source. And the ratio of this voltage to the current will give us the equivalent resistance. So for the given circuit, let's apply the test current of 1 ampere. Now arbitrarily, we can choose the current source of any value. But here, the reason for choosing a 1 ampere current is that once we find the voltage across this current source, then we just need to divide this voltage by the 1 ampere current. So basically, by choosing the 1 ampere test current, the calculation will become easier. So here, to find the voltage across this 1 ampere current source, we need to find the voltage across this 100 ohm resistor, because this 100 ohm resistor is directly in parallel with 1 ampere current source. So here, let's say the voltage at this node is Vx, while the voltage at the second node is Vy. And to find this voltage Vx, let us apply the KCL at both nodes. So at this node X, if you see, this 1 ampere current is entering the node, while the current through this 100 ohm resistor and the 50 ohm resistor is leaving the node. That means if we apply the KCL at this node, then we can write 1 ampere is equal to Vx minus 0 divided by 100 ohm plus Vx minus Vy divided by 50 ohm. And if we simplify it, then we can say that 3Vx minus 2Vy is equal to 100. And let's say this is the first expression. Similarly, now let us apply the KCL at this node. And here we are assuming that all the currents are leaving the node. So by applying the KCL, we can write voltage Vx divided by 10 plus Vy divided by 200 plus Vy minus Vx divided by 50, that is equal to 0. And if we further simplify it, then we can write 16 times Vx minus 5 times Vy is equal to 0. And let's say this is the second expression. So if we solve these two expressions, then we can find the value of this Vx. So the value of Vx will come around as 10.638 volt. So this will be the voltage across this 1 ampere current source. And if we divide this voltage by the 1 ampere current, then we can find the equivalent resistance which is seen through these two terminals. That means the Norton's equivalent resistance will be equal to Vx divided by 1 ampere, that is equal to 10.638 ohm. So this will be the equivalent resistance which is seen through these two terminals A and B. And this is the Norton's equivalent of the given circuit. So through these three different examples, I hope you understood how we can find the Norton's equivalent of the given circuit. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.